All right, we'll get started here. Again, welcome to Applied Day 2022. This is the Advanced Analysis and Engineering Simulation presentation. We'll get rolling with the presentation here shortly, but first I just want to give a quick introduction of Applied. Since 1986, Applied Engineering has been providing high-quality engineering services. We can assist you at any and all stage of the product lifecycle, whether you need help with product design, simulation and analysis, factory design, process automation, or you just need an extra set of hands to get a job done. Applied is there for you. And then additionally, we have our print and image services that allows us to offer high quality, large and small format printing and scanning services for architects, engineers, and others as well. During this session, please feel free to enter any questions you have into the questions box. I will be monitoring them throughout and I will address them as they come in. And then we'll have some time at the end for questions as well. All of the webinars today are being recorded and will be sent out to you via email. So if you want to rewatch them, you can, or if you want to share them with friends, colleagues, peers, whomever, you can do that as well. With that, I will pass things over to our presenter, Alex Sinclair.
Thanks, Emily. I'll do a quick introduction here. My name is Alex Sinclair. I am a design engineer and simulation specialist with Applied Engineering. And today we are going to be talking about advanced engineering analysis and simulation. A little bit about the agenda. We'll start off with the value proposition and talk about some key benefits. And then we'll step through all the different analysis types and capabilities that we have here at Applied. And we will also provide some examples of each. So jumping right into it, what is advanced engineering analysis? Advanced engineering analysis are different methods of analyzing how products will perform. And really, I want to hammer home the value proposition of utilizing this service here at Applied. Advanced analysis techniques enable engineers and product developers to predict design issues, thus minimizing risks during prototyping or the product's service life. And so this is really, again, where we see the value of this service for all of our customers, and we do have a lot of capability here, which we will discuss throughout the webinar. Some of the key benefits: modern simulation tools allow us to rapidly innovate and validate our products and designs. We can reduce cost and times associated with our design cycle. So if we think about, the design cycle as, design, build, test, and then we kind of iterate on that and go through it multiple times, we can really reduce, how much time we're spending on that and how many iterations we're going through by using advanced engineering analysis and simulation. So virtual prototyping and testing, I kind of already touched a little bit about that. We can do existing product optimization or even, optimize new products. And we can also estimate durability and fatigue life, and these are just to name a few of the key benefits. With that being said, though, I think we'll jump right into the different analysis types. I'll often refer to these as environments. We exclusively use the ANSYS software environment here at Applied. And so really, we'll kind of step through each different environment within the ANSYS Workbench product platform, starting off with static structural analysis. This environment enables us to determine the displacements, stresses, strains, and forces in a structure that's subject to static loads. This type of analysis is really our bread and butter here at Applied. We do this day in and day out. This environment has a ton of capability. We can take into account very complex geometry, a lot of different nonlinearities, complex contact, advanced materials, you name it. We can take it into account in this environment. Some of the applications, just to name a few here: frames and machines, this could be complex structures or weldments. We can look at consumer products and biomechanics. We can even take a look at different manufacturing processes and the equipment. Stepping into a couple of examples, the first two examples come from our friends over at Doosan Bobcat. On the left, we have a compact track loader, and on the right, we have a compact excavator. Here we can see fairly complex weldments that make up the different frames and structures of these products, including, you know, all the hydraulics and pivot points, things like that. Really, these two images are kind of showing some virtual testing that we've done to kind of simulate some real world testing that these machines would go through in their validation cycle. So some great fun projects that we've done in the past. On the bottom, we have, this is actually an aluminum flange profile that's being pressed onto a web. This project came from our friends over at 10th Avenue Rebuilders, and the goal of this was to actually determine the amount of force that is required to press that flange onto that web. And this is actually an animation, so I'll play that for us so we can kind of see the process of this flange actually being pressed on the web. We can look at the cross-sectional stresses here and determine the amount of force that it takes to push that on there. Moving on to transient structural analysis. This environment is kind of just a step further from the static environment, in which we're taking into account our dynamic loads and we're including our inertial effects. So we're going to calculate everything we calculated in the static environment, our displacements, stresses, strains, forces, but we're going to add in our velocities and our accelerations in this case. Some of the applications of this environment include drop testing, impact events, shock loading, or even transient signals from some field data that we might have collected from a load transducer or perhaps an accelerometer. The example for transient structural that I have to share here is a cab that's subject to an impact from a falling object debris. This would be considered a falling object protection system, and so we need to ensure that the operator that's sitting in this cab is protected from any types of falling object. And so we can see kind of the dynamic response of this cab to this falling object, and it's good that the object doesn't break through the cab and harm the operator here, and we can kind of see you know, the dynamic response and the stresses and strains that are induced, you know, during that time history based response with a cab. Moving on to thermal analysis. This thermal analysis comes, you know, in both the static and transient variety. Here we're determining temperatures, thermal gradients, heat flows, and heat fluxes in typically solid materials. Thermal analysis is going to be the first step in any heat-based problem that comes across our desk. Some applications include heat dissipation products, electronics. We can couple this environment with our CFD environment that we'll talk about later, and we can do some conjugate heat transfer where we're actually, you know, transferring heat from fluid to solid. Examples of thermal analysis I put together, we have on the top right here kind of a complex little heat sink shape, and on the bottom left, this is actually a coffee mug on a warmer, and so we want to make sure that not too much of our heat is getting into the main body of the cup and the handle. We want to be able to pick that cup up. Next, we have vibration analysis. This environment allows us to determine the vibration characteristics and some of the intrinsic vibrational properties of a structure. We're going to look at the dynamic response of that structure due to vibrational loads. A few applications of this include vibratory equipment, powertrain components, maybe virtual shaker table testing. There's a lot of vibrational requirements in military standards. Maybe our structure is resonating at, you know, our given applied loads, and so we need to make some changes to prevent resonance in our structure. Or maybe we just have some sinusoidal varying loads, you know, that we want to apply to the structure. Out of balance masses perhaps could be an example of that. A few examples of vibration analysis. The first one comes from our friends over at Superior Industries. This is actually an aggregate material processing screen. And so we will dump aggregate material into the inlet section of this screen. That screen will separate out different sizes of the aggregate material and, you know, eject the different sizes out the exit. On the bottom, another example from our friends over at Doosan Bobcat. This is a diesel particulate filter. This guy bolts right onto an engine, and so it's subject to the vibrational loads from the engine, and we need to make sure, you know, that our diesel particulate filter in this case, you know, doesn't vibrate right off the engine. Next environment, an analysis type that we're going to talk about is rigid body dynamic analysis. This type of analysis determines dynamic responses of an assemblage of rigid components. And some applications of this would be, you know, products that have complex kinematics. A good example of that could be a suspension system or some robotics, gear systems, or even drivetrain components. Another example could it maybe even be a vehicle that's driven over some type of obstacle course. We could take the obstacle course input and actually run that in this environment and subject our vehicle to, the displacements from the obstacle course. The example I have here is a mini Formula One front end suspension. We're going to subject this suspension to a bump, basically. So I'll animate this for us here, but we're going to run the tires over a bump and we're going to see, what the response of the chassis would be in this case. And so to me, the suspension looks a little bit undertuned. We're sagging a little bit, lower than we probably should, and we might be bottoming out. So this suspension could use a little bit better tuning. Explicit dynamics analysis is next. This type of analysis determines the dynamic response of a structure that's subject to short duration and or high intensity loads. Here we want to think of our loading, being much faster application time than the natural period of our structure. So things like explosions, ballistic impacts, or even shockwave propagation through a structure. The example I set up here is kind of neat. This is actually a 7.62 NATO round, 122 grain round fired at 2,600 feet per second. And this round is actually going to penetrate through these plates. I'll animate it here for us. I separated these plates a little bit because I wanted to be able to show the deformation and subsequent failure of the plates as the round goes through. There is a significant amount of structural integrity lost by spacing the plates apart, but I think it really shows kind of, the capability of this type of analysis here. Next analysis type is fluid dynamics, commonly known as CFD or computational fluid dynamics. This type of analysis allows us to determine the flow characteristics, the heat and mass transfer phenomena, and chemical reactions within a flow, to name a few. Ton of applications of this. This is a widely used type of analysis in industry. Again, some applications, internal, external flow, that pretty much covers everything. But, if we want to narrow that down a little bit, we could look at aerodynamics, rotating machinery, HVAC systems, heat transfer, conjugate heat transfer. We kind of already talked a little bit about those in the heat transfer FEM slide. Maybe we have a couple different fluids of different temperatures mixing together. That would kind of be the heat transfer piece, or we're maybe even including some solid components. So we're going to take a look at the heat transfer from liquid to solid, electronics cooling, and we can even do reactive flows. Example of that would be combustion. The example of the fluid dynamics project I have here, this is a shell and tube heat exchanger. And so here we can take a look. The inlet of this shell and tube heat exchangers on the bottom left, we have hot fluid coming in. It flows through the heat exchanger out to the top right where we have cooler fluid exiting. If we take a cross section of that, we can see the tube, the cooling tube that's inside this heat exchanger, and we can kind of see the temperature contour, as the fluid flows from the inlet to the outlet. So again, an example of computational fluid dynamics here. Next type of analysis, polymer flow and polymer processing. Here we're going to be determining the behavior of viscoelastic materials for many common manufacturing and processing methods. Extrusion, co-extrusion, blow molding, thermoforming. All these manufacturing processes can be simulated in this environment. What this environment is really good at is taking a look at the actual design of the die that shapes our different extrudants. Okay, and I do have an example for this. What we're looking at here is a die, an extrusion die, and so we have material flowing into this die on the bottom left from an extruder. This is half the die. This is a symmetric model, so we're only looking at half the die. The polymer flows through this die and out. The die lip on the other end, and so that's where everything after that die lip would be considered the extrudate, or the final shape of our extrudate, our extrusion material. This is a co-extrusion problem. So what we're doing here is coating a metal insert with some polymer. And we can see at the end of the die lip there that our velocities speed up a little bit. And we can even see the die swell of our polymer as it exits the die. If we look at a close-up of this, this is a velocity contour close-up at the die lip. We can see that our dye is not very balanced. We have some large velocity gradients in the exit section, so this could lead to some quality control issues. And the black line that's kind of surrounding our velocity contour is actually the outer edge of our extrude profile. So that's kind of, again, really outlining the polymer swell as it exits the dye there. So a lot of capability in this environment, a lot of different polymer processing examples that we can simulate here. Next is particle flow dynamics. This type of analysis is also known as DEM, or discrete element modeling. Advanced DEM particle dynamics for industrial applications. Here we can use take into account custom particle shapes. We can model breakage of the particles, adhesion of one particle to another, and just the overall flow dynamics of these particles. Some examples of some different particle flows could be rocks or other aggregate materials, pharmaceutical products, foodstuffs, or really any product that's subject to a moving logistical process. Applications, material handling, mixing, crushing, material blockage in some kind of logistical chute, maybe conveyor chute. We can simulate agricultural processes here, or even pharmaceutical processes. The example for particle flow that I have is actually just some bulk material being piled by a conveyor. And so I'll animate this here, but here we're just modeling some different size. We call them rocks. They're kind of just assumed to be spherical in shape, but we're just piling them using this conveyor. The animation here is sped up a little bit so that we can kind of see it faster than real time, but very capable software, the DEM software. We can model a lot of different industrial processes with this. I'll kind of end by just touching briefly on coupled systems. We've kind of touched on this on a few of the previous slides, but coupled systems enables, well, you got it, the coupling between different analysis types. And so some applications, maybe fluid structure interaction, maybe we have some fluid flow around a structure, and we want to actually look at the flow force on the structure, or maybe the wind force on the structure that we're calculating in that fluid flow analysis. We can do that. We've already touched a little bit on conjugate heat transfer between solids and fluids, but we could take that a step further and even look at the thermal stresses in the solids due to that conjugate heat transfer. The previous slide, we talked a little bit about the particle flow. We could take a look at that particle flow and those particle interactions and couple that to a fluid flow. One of the examples I've seen there is cutting grass and then actually pushing that flow of the air grass mixture out of the grass cutter. So kind of an interesting example. But with that, that kind of wraps up all of our different analysis types, and we've gone through quite a few examples. But we started with our value proposition and some of the key benefits of advanced engineering analysis and simulation. Then we stepped through again all our types, capabilities, and went through some examples. And I hope everybody enjoyed this webinar this afternoon. And with that, I'll turn it back to Emily.
Thank you, Alex. I don't see any questions in the questions box as of right now, but if you have any, please feel free to drop them in there while I'm kind of giving my little outro spiel today. Otherwise, obviously, you can email Alex or anyone at Applied, really, if you have questions about our capabilities. I just want to thank everyone for attending today. We have one more session this afternoon starting at 2 p.m. And that is going to be our What's New in Applications Development presentation. So be sure to tune into that one. And then again, all of these sessions are being recorded and will be sent out to you via email. And they will also be available on our YouTube channel. So that is all from us today. Thank you again for attending.